Our next section is on least squares regression. In this section, we'll look at interpreting a regression line, calculating the equation of least squares regression lines, calculating residuals, looking at residual plots, determining how well a line fits observed data, and interpreting computer regression outputs. A regression line is a straight line relationship or linear relationship between two quantitative variables. It summarizes the relationship between two variables, but only in settings where one of the variables helps explain or predict the other. It describes how a response variable y changes as an explanatory variable x changes. We often use it to predict the value of y for a given value of x. Here's an example of a scatter plot. The plot shows a moderately strong negative linear association between NEA change and fat gain with no outliers. The regression line predicts fat gain from change in the NEA. As you can see, here's an example. When non-exercise activity equals 800, our line predicts a fat gain of about 0.8 kilograms after 8 weeks. Here's another example. The following data shows the number of miles driven and advertised price for 11 used Honda CR-Vs from 2002 through 2006. The scatter plot shows a strong negative linear association between number of miles and advertised cost. The correlation is negative 0.874. The line on the plot is the regression line for predicting advertised price based on number of miles. A regression line is a model for data. It gives a compact mathematical description of what the model tells us about the relationship between our response variable y and the explanatory variable x. Therefore, a regression line, because it's a predicted value, is given as y hat, which is predicted value of the response variable for a given value of the explanatory variable x. B stands for the slope, which is the amount by which y is predicted to change when x increases by 1 unit, and A is the y-intercept, the predicted value of y when x is equal to 0. So our equation y hat equals a plus bx. Here's just a side note. On the AP exam formula sheet, the least squares regression line is written as y hat equals b sub 0 plus b sub 1 x. Formulas for the slope b sub 1 and the y-intercept b sub 0 of the least squares regression line also use this notation. So instead of a plus bx, which is the same way we'll see it in the graphing calculators, they use b0 and b1. Just keep that in mind. Consider a regression line from the example, does fidgeting keep you slim? Identify the slope and y-intercept each value has in the context. So here it is in context. Our y hat, which is fat gain, equals, here's our equation for our regression line, 3.505 minus 0.00344 times the amount of non-exercise activity change. Our slope tells us the amount of fat gained is predicted to go down for each added calorie. The y-intercept, A equals 3.505, is the fat gain estimated by the model if the non-exercise activity does not change when a person overeats. Here's another example. We have y hat, our price, equals 18,773 minus 86.18 times number of miles. So our equation, if we put this in, here would be our y hat, our number of miles would become our x. Our slope then would be the number with the x, 86.18 The y-intercept would be the 18,773. Another AP exam note, make sure to state the slope is the predicted or estimated or expected change in the y variable for each increase of 1 unit in x. You're going to have to understand the difference between the actual data and the equation used to model the data. You can't say how important a relationship is by looking at the size of the slope of the regression line. We can use a regression line to predict the response y hat for a specific value of the explanatory variable x. Here's an example. We have the predicted fat gain for a subject with our NEA, non-exercise activity, equal to 400 calories. To predict the amount, we plug the number 400 in place of the non-exercise activity change, which is our x value. So our predicted y hat value, when we plug in the number, is 2.13. So we predict a fat gain of 2.13 kilograms when a person with non-exercise activity is equal to 400 calories. Back to our example, again with the equation of the Hondas. To predict the asking price for a car with 50,000 miles, we would plug in 50,000 miles, that's our x, remember, into the parentheses here. That would be multiplied, and that would give us our predicted value. We can also look at the graph to see, according to the line, what the predicted value cost approximately would be. One of the things we can use for the predicted value and using the regression equation is to use what's called extrapolation. This is where we want to figure out a value based on the regression line and predicted values. So it's the use of the regression line for making predictions far outside the interval of values that we use to obtain the equation of the line. Just a side note, don't make predictions using values of x that are much larger or smaller than those that actually appear in your data. So in other words, when you use extrapolation, be real careful that you're not predicting too far out. So here's an example. Should we predict the asking price for a used 2002 to 2006 Honda CR-V with 250,000 miles? As you can see, our line goes to 90,000 miles. So it would not be a good idea to make a prediction this far out, which is 250,000 miles from the graph. A residual is the difference between an observed value of the response variable and the value predicted by the regression line. To find a residual, we take the observed y minus the predicted y value. So in other words, we take the actual y value from the graph and subtract it from the predicted y, which is on the line itself. So our equation for residual is taking y, observed y, minus y hat, predicted y. Here you can see an example. Here's the regression line that we would use for this data that's calculated. We have the vertical deviation from the line, or vertical distance in other words, from the data point to the line. The actual y value minus the y predicted value, which is on the regression line, would give us the residual value. As we can see then, positive residuals are above the line, and negative residuals would end up being below the line for our line of best fit or regression line. Different regression lines produce different residuals. The residual line we want is the one that minimizes the sum of the squared residuals. The least squares regression line of y on x then is the line that makes the sum of the squared residuals as small as possible. So here you can see the least squares regression line minimizing the sum of the squared residuals. So in other words, if we take the value and we square the residual value again, we want it to be so that the sum of the squared residuals is as small as possible. So we want this residual value, when we square it, remember it becomes positive we want those values to be small when we add all the values together. In other words, we want our points of data to be close to the regression line. So we use technology to find the equation of the least squares regression line. We can also write it in terms of mean and standard deviation of the two variables and their correlation. So our equation of the least squares regression line, we calculate the least squares regression line is the line y hat equals a plus bx. We can also calculate it with slope. So to use or find the slope, to get b, in other words, in the problem, we can use r, which is our correlation, s sub y, standard deviation of y, over standard deviation of x. And to get the y-intercept, which is the a value, again, we can use other values such as our mean y bar minus b, we'll calculate b from up here, times x bar. So these are just different ways to calculate and get a and b if we know the mean and standard deviation and the correlation. Here's another example. We have the asking prices for our Hondas, a mean of $14,425. The mean for 11 used Hondas is 50.5, a standard deviation of 19.3, and this is in number of miles in thousands. And the standard deviation is $1,899. The correlation was R equals negative 0.874. We want to find the equation of the least squares regression line and explain what change in price we would predict for each additional 19.3 thousand miles. So to get our answer, we find the slope b by taking r, negative 0.874, times the 1899, which is the standard deviation of the y, over the 19.3, which was the standard deviation of x. Remember, x was the number of miles in thousands, y was our price. And we get negative 0.86. To find and interpret the a value, we take our 14,425, which was the mean of the price, minus negative 0.86, our b value, times the 50.5, which was the mean of the x value. And we get our a value. So we would expect the cost to change by negative 0.874 times 18.99, or negative 1,660 for each additional 19.3 thousand miles. A residual plot is a scatter plot of the residuals against the explanatory variable. Remember, explanatories are x variable. They help us assess how well a regression line fits the data. Here's an example back from our non-exercise activity example versus vacuum in kilograms. Here's the same thing, same x value versus a residual graph. Remember, the residual graph tells us how we're going to assess a regression line and how well it actually fits the data. A residual plot magnifies the deviations of the plots from the line, making it easier to understand unusual observations and patterns. The residual plot then should show no obvious patterns. They should be relatively small in size. So patterns in residual plots tell us that the linear model is not an appropriate model for the data. If we use a least squares regression line to predict the values of a response variable y from an explanatory variable x, the standard deviation of the residuals then can be found by the following. We take, remember, square root for any kind of standard deviation, and we'll take the residual squared, which was our observed minus predicted value to get the residual squared, divided by number of observations minus 2. Here's a scatter plot showing the number of miles and asking price for 11 used Honda CR-Vs. The least squares regression line, which we've already calculated earlier, is shown on the scatter plot. The car circled in the plot below has 70,000 miles and an asking price of $14,450. The predicted asking price is $12,740. The residual is therefore y minus y hat, which was 14,450 minus the 12,740, which equals 1,710. The residual is positive since the plot lies above the line. Then here's the scatter plot and residual plot for the used Honda's data. The standard deviation, we take the square root of our, remember we had 11 observations, so minus 2, and then this was our sum of the values, so we get 972 values. So when we use the number of miles to estimate the asking price, we will be off by an average of $972. So the standard deviation of residuals gives us a numerical estimate of the average size of our prediction errors. There is another numerical quantity that tells us how well the least squares regression line predicts values of the response y, and that's the coefficient of determination. R squared is the fraction of variation in the values of y that is accounted for by the least squares regression line. We can calculate R squared using our formula. So we have R squared equals 1 minus, and then we have our SSE over SST. SSE is the sum of the residual squared, and SST is the sum of our observed minus our y value, observed y value, minus the mean squared. Here's another example. Again, going back to what we had, they give us the values of the SSE and the SST, and therefore we can figure out our answer is a percentage, which at the end we get 76.4% of variation in asking price is accounted for by the linear model relating asking price to number of miles driven. Here's an example just showing again the difference in the two types of sum of squares variations. R squared then tells us how much better the least squares regression line does at predicting values of y than simply guessing the mean y for each value in the data set. If we needed to predict a backpack weight for a new hiker but didn't know how each hiker's weight or what it was, we could use the average backpack weight as our prediction. The sum of the squared residuals is given as 83.87. If we use the least squares regression line, the sum of the squared residuals was 30.90. So we have our SST and our SSE, which is again the sum of the squares residuals versus the sum of the squares residuals from our predicted values. If we divide those, we get 0.368 or 36.8 of the variation in backpack weight is unaccounted for by the least squares regression line. And 63.2% of the variation is accounted for by the linear model relating backpack weight to body weight. One of the things then we'll get is a lot of information on computer output software, so we can locate the slope, the y-intercept, the values of s and r squared. So here it's showing us standard deviation of the residuals, the r squared value, and then our slope and our y-intercept. You'll have to be able to recognize and pick out the numbers from computer output. Here's just some other ways that it can be shown. Again, a different way, so this is Minitab, this is from a different computer program. Again, you look for the r squared, that's this value. You look for, in this case, it's the root mean square error, which is simply just s. That's the same as this s value, or standard deviation of residuals. And then we have the y-intercept and the slope again. And this time it says intercept, where it's the y-intercept. And then we're looking again for the slope is the amount of change, same as over here. So this is again just two different computer outputs. Here's another example of, again, looking at a computer output. So we have our values we can read right from the computer output. Our equation of the regression line, y hat equals the 181.2, which is right here from the data, 15.2, which is right here from the data. That will give us that. The slope tells us that for each additional tablespoon of sugar, the flours are predicted to stay fresh an additional 15.2 hours. The correlation would be the square root of the 0.860. Notice that this is the r squared, so to get r we have to take the square root. Notice also this is in a percentage. We want to change it to a decimal. So our distinction between explanatory and response variables is important in regression. Correlation and regression lines describe only linear relationships. Correlation and least squares regression lines are not resistant. And then here's an example again with the different values without some of the different children versus with. Remember, an outlier is an observation that lies outside the overall pattern of the other observations. Points that are outliers in the y direction but not in the x direction of a scatter plot have large residuals. Other outliers may not have large residuals. An observation is influential for statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the x direction are often influential for the least squares regression line. So now we have to look at whether it's an outlier or whether it's a point that is simply influential. Association does not imply causation. Here's our summary. Take a look at the different points in the summary that we've talked about in the lesson. Our next lesson, and looking ahead, we're going to start looking at experiments and surveys and sampling and how to use studies wisely.